Hello everyone and welcome to the final day of the Edyst December 2020 Daily Challenges. For those of you who are not aware, Edyst has been running December Daily Challenges started on December 7th and we've reached the end, which is December 11th today. Basically, every day starting on 7th December, we launched one particular challenge at 6 p.m. on the Edyst platform itself, and you could actually check out this challenge on the link given above, which you can still go ahead and start now, but all the challenges are over currently. The new challenge opens up every day at 6 p.m. and the solution is released at the same day at 9 p.m. So today, while we're releasing the solution, it is the last solution for this series. The first to crack the challenge is on top of the leaderboard. So we're going to check out the leaderboard and announce in a separate video who's the winner, etc. And also this is, as I've continuously said, it's ideal for students preparing for product companies because a lot of people get scared of dynamic programming. Why did I say dynamic programming? Because that is the theme for this December daily challenges. In fact, if anything, I very hopeful that by the end of this 5 days, you've at least been able to solve at least one problem and understood that maybe dynamic programming isn't really that difficult. It requires a lot of thinking and a lot of practice, but it's not something that's like a black magic that you'll never end up getting. And I hope you've at least got some feel for dynamic programming, and if you want to like get better at it and you want to work even harder on it, do sign up for our advanced algorithms and data structures bootcamp led by me as an instructor, and also some really other great instructors as well. As part of this bootcamp, we cover all of the previously asked questions of Google, Microsoft, Facebook. Basically all of these companies ask questions on dynamic programming and much more, so we cover all of those topics. We've given in detail about this bootcamp on our YouTube channel, so go ahead and check it out on our channel as well. To high performing students, we also give referrals to certain companies, and we also run industry awareness sessions as well, and much more. Do check out our videos on this to know more about it. It is a paid bootcamp, but these December daily challenges were completely free. So if you've made the most of it, I hope you have, and you can actually start doing them. And if you did not have the chance, these challenges are open to you even right now. Go ahead and try them out and then view all of the solutions, because all of the challenges have had a solution. And including the one today, which is what we're going to discuss today. So today's question, day 5 question, is called maximum tree sum. Some people were asking, why didn't we do like a 7-day or 10-day challenge? My answer would be, if you were able to solve day 5 question, I think you should be happy, because a lot of people weren't able to, and 5 days of dynamic programming is more than enough just to get an introduction on it. Anyway, so this question is max tree sum. I'm going to open it up on the Edyst platform. So let's have a look at it over there and then get started. Okay, so you're given a tree, and I think already a lot of people have got scared because of the trees, but don't worry about it. It's, if you understand tree and if you understand how it's going on, I'll try my best to make you understand. Okay, so let's not even say that if you understand, we'll try our best to make you understand. So you're given a tree of n vertices. We have to choose the elements of this tree in a particular order. So you can choose it in some order. Initially all the trees are painted white, or all the vertices are painted white. We need to choose a vertex and paint it red. From then on, we can only choose vertices which are neighbors of red vertices. So first I can choose one vertex and I can paint it red, and then from then on I can only choose neighbors of that vertex, or any vertex whose color is already red. We get some points when painting a vertex red. These points are calculated as the total number of connected white vertices to this current red vertex. Okay, the game finally ends when there are no more vertices to paint red. What does this all mean? Let's look at one example ourselves. I'll just explain this in an example. You could also check out the example explanation given in the question, but I'll just go ahead and explain another example to all of you. So this is the tree that's given even in the question. Okay, this is a tree, and let's just try out a random order, right? It says I can paint something red, and when I paint that red, I get the points of all of the connected white components. What's exactly happening over there? So what's happening here is, I paint, let's say I want to start and paint one red. So if I paint one red over here, what I'm going to get is not only one, but I will get the size of all of the connected white components to that one before I painted it. Okay, so before I painted it, how many elements were connected to one? There were, like, the size of that entire component was 9. If you look at it, 1 2 this 3, so like there are totally 9 vertices, right? So 1 2 3 4 5. So there were 4 vertices here, there were about 4 vertices here, and 1 itself. So there were 9 vertices. So the moment I painted 1, I got 9 points, because it was full of a connection of, or it's a component of white vertices, 9 white vertices before I painted one. Now I can either choose 2 or I could choose 4, because now from now on I can only choose neighbors of a red vertex. So let's say I choose 4. Okay, so if I choose 4, what do I get? I get the entire points of how many elements were connected, including 4. So including 4, there were 4 points connected, right? There was 4, 9, 7 and 8. 4 vertices were connected. So if I paint 4 red, I'm going to get the points for 4, 9, 7 and 8. I would have also gotten 4 if I would have done 2, 5, 3, 6, right? So if I painted 2, I would have still got 4 points over there. So that's not much of a difference there. I can choose 4, I can choose 2. So I chose 4 over here. Okay, so my total points would be, on selecting 1, I got 9 points. On selecting 4, I got 4 points. By the way, selecting a vertex and the points I get from that vertex has nothing to do with the number on the vertex. So it just so happens that we got 4 points here from the vertex 4, but it doesn't always be the case. We look at it in the next one as well. Let's say I paint 9, okay? Because now the only choices I have are, I could either paint 2 or I could paint 9. Eventually I'll have to paint 2 anyway, so let's just go down and paint 9 itself, right? When I paint 9, I get 3 points, because 9 in itself is part of connected components, that is 9, 7, 8. So I get 3 points from that. Now I can either paint 8, 7 or 2, because these are the only neighbors of red vertices remaining. So let's say I paint 8 and then I paint 7. Each of these will get 1 point each. This is the interesting part. When I painted 9, I got 3 points because these were the 3 connected components. When I painted 8, this part here was only 1 connected component. It's not connected to 7 because there's a red in the middle, right? So there was only 1 connected component here, 8. And then I again painted 7, so I got 1 more point for it. So I got totally so far points 9 plus 4 plus 3 plus 1 plus 1. Let me go and paint 2, which will give me 4 points. Okay, then when I paint 5, 3 and 6, each of them are going to give me 1 point each, and the sum of this entire thing becomes 25. So if I went in this order, I painted 1 first, then 4, then 9, then 8, then 7, then 2, then 5, 3, 6, my total sum would be 25. Now the question says, and it's given in the question explanation, that actually there's a better order of painting it. Okay, and that order is actually if you start from 7, and it only makes sense because you want to keep as big a connected component ready with you as possible, right? So for example, if I paint this one 7, right, as red, let me just paint it red. So I paint this as red, right? So how many points did I get for painting 7? I will get 9, because on the first try I'm always going to get 9 points, right? Because the entire thing is connected. Then I can paint only 9 because the only neighbor I have to 7 is 9. So let's say I paint this. What do I get? Then the total number of points I get is 8, right? Because 8, 9, 4, 1, 2, 5, 3, 6 all are connected. Okay. Then what I could do is paint 8 or 4. I have to eventually paint 8 anyway, so let's paint it right away. And for this one I get only 1 point, so I don't get much for it, but I get 1 point here. Then what happens if I paint 4? Yeah, I'll have to paint 4. That's the only one right now. If I paint 4, I get 1, 2, 3, 4, 5, 6. So there are like 6 elements here. I get 6 points on painting 4. Let me paint 4. Then let's paint 1. That's the only thing I can paint right now. So I go and paint 1. For 1, I will get 5 points. So I got 5 points here. Then I have to paint 2. Right. So I paint 2. On painting 2, how many points do I get? I get 4 points. Then I'll get 1 plus 1 plus 1, right? So painting 5, 3, 6 is going to give me 1 point each, right? So I get that. So finally the sum I get is 9 plus 8 is 17, 17 plus 1 is 18, plus 6 24, plus 5 29, 29 plus 4 33, 33, 34, 35, 36. So this sum is 36, and if you look at the previous one, it was 25. So finally all of them are painted, but in the new one I'm getting 36 points, whereas in the previous one I was getting 25 points. And that's exactly the order in which the question also tells us to do. So I hope you now understood. So this is the tree that was drawn, and now at least we got that this is the order in which we are supposed to do, and these are the points. We would have got total 36 points. Your answer has to be this total 36. You don't actually have to print out the order in which you're supposed to print it, but you're supposed to print out what's going to be the final answer, what's going to be your final sum, okay, and how to do it. Okay, all right. So I hope you've understood the question now. The question has become clearer. I hope so. So already, if we want to think about how to solve this question, one naive approach or basic approach that we can think of is that try taking each node as a starting point and calculate the points, right? So take the first node and like take one and try to calculate the points, because when you paint one, then you can only paint any of its neighbors 2 and 3, and then I mean, like, is it 2 and 3? Yeah, no, sorry, 4 and 2, and so on. So you can only paint the neighbors, and then you can only paint their neighbors, and so on. So finally, you can try out multiple ways, and you can get it. So the like for example, in here, let's go back to our original tree, right? Start with go even further. Start with 1, then try 2 4, 4 2 4. Then there's only one thing you can try here. But let's say if I start with 4, then I can then go to 1, then I can go to 9, then I can go to 7 8, and so on. So I could start itself with 3, because there's no need to actually start with a particular one. So I could start with 3 and then go to 5 to 6 to 2 and so on. So I could do that as well, right? So one naive approach is try out all the possibilities, right, and see what happens. What you've hopefully learned so far is, even before you try out the naive possibility or the basic possibility, look at the constraints. And if I check the constraints, what it basically means is there are roughly there could be up to 10 raised to 5 vertices. If there are 10 raised to 5 vertices, then how many ways are there for me to go about? Well, the thing is, let's say if there are 10 raised to 5 vertices and each one of those vertices could be a starting point, then we have to traverse all the vertices anyways for each of these 10 raised to 5 vertices. So if I take 1, I'm going to traverse all the vertices, and then I'm going to take 2, I'm going to traverse all the vertices. So for each 10 raised to 5 vertex, I'm going to traverse 10 raised to 5 other vertexes. It's going to be a power 10 raised to 10. I can't really afford 10 raised to 10 over here, right? In fact, when it's 10 raised to 5, which I hope you would have understood by now, is that the max you could go is 10 raised to 6 roughly. That's the thing you can go. I need a way of figuring out how to do this in one pass, right? Or in 2 passes. Basically, I need to go through all of the vertices once or twice or thrice at max, and I should be able to get the answer. Anything more than that, like if I'm doing even like n log n, okay, log n may just work out, but in all other cases, n square, that's 10 raised to 10, it's too much. I can't really do that. So we need to think of a better way on how to do this. And what would that better way be? Well, let's make one observation to find out that better way. And the observation mainly is, it's a very simple observation, but also a profound observation. It depends on which element we start with, because if I start with 1, I have to choose its neighbors. If I start with 7, I have to choose its neighbors in the next go. So depending on which element I start with, my calculation will change. Now the point is, the relation between starting with one element or the other element is not completely different, that once I calculate one element, I have to completely remove it and calculate for another element starting, right? What do I mean by this? Let's say, for example, we had let's take our original tree here, right? And we started from 1. So let's say we started from 1 and we calculated everything, right? And while we are calculating, we were also a little bit smart, and we stored, okay, what is the size of this particular subtree? What is the size of this particular subtree? So like, for example, size of this subtree is 1, right? Size of this subtree is 1, right? Size of this subtree is 3, because I'm going to include 9 itself in it. Similarly, the size of this subtree is 4. I'm going to include the 4 itself in it. What is the size of this subtree? It is, this 4 elements plus this 4 elements plus 1 itself. So it is 9 over here. What is the size of this subtree? The size of this subtree is 4, because I want to include 2 as well. And the size of this subtree is 1. And I'm just going to paste that here. Right. So these are the size of the subtrees. Okay. So yeah. So these are the size of the subtrees that we have. Okay. Sorry for that. So these are the size of the subtrees. And now what I can basically note is, if I start with 1, what I need to do is choose either this subtree or this subtree to paint. And in fact, eventually I'll end up choosing both the subtrees. But the point I'm trying to make here is, okay, I calculated for 1, I have to like take this subtree. So what that would be is like, I pick up like 4 plus then the score of this subtree, right? So essentially what I'm trying to do is, I'm going to take, like, for example, I take 4, right? So when I painted 1, I got 9 points because of its entire subtree. Then when I painted 4, I got 4 points because of its subtree, and I'll keep going down and keep getting the other subtrees as well, right? So finally it becomes like 9 plus 4 plus 3 plus 1 plus 1. And if I'm not mistaken, that is exactly our calculation as well, right? 9 plus 4 plus 3 plus 1 plus 1. That's what we got, right? Similarly here we would have got 4 plus 1 plus 1 plus 1. So if I take the sum of all of this, it becomes like 1 1, these are like 5 1, so it becomes 5 plus 3 8 plus 4 12 plus 4 16 plus 9 25, right? Which is what this was the score when we had initially taken that I want to paint 1 in itself, right? So basically it was just the sum of all of the subtrees that I got here. So anyways, what I'm trying to impress upon you here is that, okay, I could start with this one and I could calculate that, okay, starting from this gives me 25 as a sum. Okay, I say, okay, that's great. Now what happens if I want to start from 4? I don't need to recalculate the entire thing again. Instead, I can just use the relation, okay, let's try to do it from 4. But when we are trying to do it from 4, what I will need to do is, this 1 no longer is 9 actually. Because if I'm starting from 4, I have to remove this 5 thing, right? And I have, like, sorry, not 5. Yeah, I have to remove this 5 over here, right? Because for this one, when I choose it next time, this 4 would have already been painted red. So when I choose one, I have to remove this, whatever was there. So sorry, not 5, I have to remove 4 because there are 4 elements. 9 minus 4, that means this one score now becomes 5. There are only 5 elements allowed over here. So that's one thing that when I have to do this, when I'm choosing this 4, I'll make this only 5. Okay, that's great. What else are the other differences? Well, this 4 no longer is 4, it's actually 9. So the score I took away from 1 has to be given to 4 itself, or rather the subtree size that I took away from 1 has to be given to 4 itself. That's what is going to happen over here, right? And this has to continue. So I did this, and then now I calculate the remaining parts, like what is the entire sum, etc., right? And we get that. And then I again try to do with 9, but this time with 9, what I'm going to do is, for 4, now I have to remove some, so then I again make it back to its original level before moving on to 9. So I'll make this 4, I will make this 9. Now if I wanted to make this 3, what I need to do is I need to again rework on this 4, remove certain value from 4. Yeah, no, sorry. If I wanted to start from here, then this 4 is no longer 4, but rather this 4 has to be considered as there are 4, yeah, this has to be considered as 6, and this has to continue to be considered as 5, right? Because this has 5 subtrees, this has to be considered as 6 because it has 6 elements in it. And when I choose this, actually this has to be considered as 9, because if I choose this as the first one, then it has to be considered as 9. So basically, between, let's say I calculated it for one tree, I should then be able to go ahead and calculate it for other elements being started as well, as long as I know that, okay, starting from this particular tree or this particular vertex helped me out in this way. Now if I'm going to start from another vertex, then I have to remove some of the previous subtree and increase this subtree and so on. So that's what I will need to do, right? So how do we do it now? I mean, diagrammatically we can do a bunch of things, but let's do it in code to understand how exactly it's going to happen. And the order here is at least the order of execution is super important over here. So let's go step by step, one by one, and try to implement this one. I'll just reset the code. I was also trying myself some things. Okay, first things first, I'm going to do it in Python, but again, same thing applies in all of your programming language, and it'll become easier for you to understand. Okay, so instead of giving you the whole logic first, I'm just going to code it in front of you and explain to you word by word what's happening. First thing I'm going to do is keep an adjacency matrix. This is one of the standard things that we need to do in terms of in any graph or tree question. So I'm going to keep an adjacency matrix. The other thing that I'm also going to do is keep a subtree size matrix. Okay, so this will count what's the size of the particular subtree. Okay, so I'm going to do that. Subtree size is equal to 0. Initially, this is initially, and when we take input, then we'll initialize this to an even bigger thing. Okay, I think that's all I'll start with, and then I'll keep adding one or two things, right? So n is equal to input. These are the number of vertices I have. Then what I'm going to do is, for I in range n, right, I want to initialize this adjacency matrix. Adjacency I is equal to this. So what I'm saying is that each element right now has 0 neighbors, or has an empty list of neighbors. That's all I'm saying right now. Okay, and let's make this 1 to n plus 1, because the numbers will be from 1 to n, so this should be n plus 1. Okay, so we got this. Then the other thing that we need to do is we need to actually create the adjacencies for all of them, right? So how many edges will we have? So we will have roughly about n minus 1 edges is what they've said, right? in the input it says, if I go here, the next n-1 line describe the edges of the tree. So I'm going to go to n-1. So for edges in range n-1, so there are about n-1 edges. What we want to do is the vertex 1 comma vertex 2 will be given to us. List map int import dot split. That's how many vertices. So those two vertices will be given. Adjacency of v1 is equal to adjacency of v1 dot append v2. So we are saying that, okay, make one of the neighbors of v1 is v2, add v2 to its list, and one of the neighbors of v2 is v1, so add this to its list as well. These are the two things that you're going to do. Okay, all right. So once this is done, next thing what we want to do is we want to calculate the, so now the tree is made and we just want to choose one random number or one random vertex and paint it red and then see what happens, right? So we'll paint that particular vertex red, and once we paint that vertex red, we'll basically store two things. One is what is the subtree size of each node, and also what's the score of each node. Okay, so this is the second thing that we're going to score. So as we stored here, that we stored the subtree size. So I'll just go back. Let's say I start from 1, so this will be 9, this will be 4, and this will be 3, right? So I'm going to store this, but not only am I going to store this, I also want to store what's the score of each, right? So if I start from 1, my score I should be able to store as 25, right? Yeah, I want to store it as 25 over here. For 4, I should be, if I start from 4, I should be able to store whatever the score is over here from starting from 4. But initially, like if I start from 1, the score of this one would be how much? Choosing this 4 itself plus 3 plus 1 plus 1, right? So 3 plus 1, it's, so this should roughly be 4 plus 3. Yeah, this would be 9, right? This, and so this score of choosing the 9 would be 3 plus 1 plus 1, 5. This would be 1, and this would also be 1, right? What are these scores? I'll just come to you and I'll explain what this is. The score of choosing this would be 4 itself plus 1 plus 1 plus 1. So it would be like 1 second. Did I make a mistake? Sorry. This would be, the score of this would be choosing 4 itself plus 1 plus 1 plus 1. So that should come until 7, if I'm not mistaken. Yeah. Okay. And 1 here is, this is also 1, by the way. This is also 1, right? I think I made a mistake somewhere, because this 9 plus, okay, correct. No, we've got it correctly, because the score, yeah. So I'll show you how this all adds up. By the way, this beautifully adds up. So we got, let's say we painted 1. What do we get? We get 9, its own subtree size, plus the score on the left side, plus the score on the right side. Okay, the score on the left side is 9, the score on the right side is 7. So 9 plus 7, 16, plus subtree itself will give us 25. Okay, how did we get this score? We just simply added all of the subtrees. So basically, apart from storing the subtree size of all of them, we will also store the score of each of the trees. So when I'm going to calculate the score of 1, all I need to do is add its own subtree size and the two scores of its neighbors. Instead of adding the subtree sizes of the neighbors, I'm just going to add the scores of its neighbors, right? So I'm going to store that value as well. I hope you got this part. If you didn't, let us know in the chat or in the comments below. We're happy to explain more. There'll be an editorial on this as well, which you can follow again and again. And again, this question is day 5. It's the toughest one. You need to spend a little bit of time to think through it completely. Okay. So anyway, so what we're going to have is both the score as well as the subtree size. So I'm going to say, okay, even store the score is equal to initially 0. And now, or actually initially just an empty list. And when we start our program, let's actually initialize it. So we're going to say subtree underscore size, subtree underscore size here is equal to 0 into n plus 1, just to have one based index A. And again, we'll do score is equal to 0 into n plus 1. Okay, so we're going to do that. And now we just want to do one depth first search. We'll do one particular depth first search. That is, we'll start from the start and we'll keep going down. And as and when we keep going down, we'll update the score, etc. So let's do dfs and update. Let's create a function called dfs and update. And in this function, what I'm going to do is, in dfs, what do I do? Depth first search, what do I generally do? I just pass a particular node and a parent. So let's say I pass 1 and I pass the parent as, let's say, -1, right? It has no parent. Basically, I'm just starting from 1 itself, right? Now the 1 could have a parent, but my point is that, and in fact every element has a parent because they're all connected. It's going to form a tree, right? That's what the question says. But what I'm trying to say here is, let's start with 1 and say that when we say -1, it means we're not giving it any parent. We're saying this is the start point itself, right? Let's define this function, and those are global variables above, so let's keep those as those. So dfs update, let's define this, and it has a node and it has a parent. Okay, and what we're going to do is for neighbor in adjacency of node. So we're going to go through all of the neighbors. One of the neighbors would be a parent. So if neighbor not equal to parents, because we don't want to go again through that. How dfs would generally happen is dfs and update, we would just go to the next node, which is neighbor, right? Neighbor, and its parent is this node. So I came from this node and I go to that particular thing. It will keep going down till I have leaf nodes or nodes which have no neighbors, right? It will keep going on and then it will come back up again. So this is how it would generally happen, but this is not sufficient for us because we want to calculate the subtree size of each one of them. So what I'll do is, whenever I visit a node, I mark its subtree size. Okay, so subtree underscore size is equal to 1. That's what I do. I will mark its subtree size is equal to some value 1 over here. Okay, not some value, it is 1 value. And if it's at the leaf node, then it's going to always remain 1. And I'm going to update the subtree size now. So subtree underscore size of this particular node is equal to subtree underscore size of the node itself plus the subtree underscore size of the neighbor. So what is happening here? Again, no voodoo is happening here. Simply put, what we're doing is we're going down over here. This updates to 1, this updates to 1. When we come here, this was already 1. We want to add 1 plus 1, because 1 it was already, because it in itself is a subtree, and we want to add 1 and 1 of these two to make it 1 plus 1 plus 1 to make it 3. That's what we did over here. So that's exactly what we are doing over here as well. Subtree size of node, we just want to increase it by the size of its neighbors. Okay, great, we did this. Then we should also do one thing. While we are updating the subtree size, we should also update the score of it, right? Let's update the score as well. So whatever was the score of this node is equal to score of the node plus score of the neighbor, right? So whatever is the score of the particular neighbor, we're going to just update it with that as well. Okay, yeah, so we're going to update it with that. And once we are done with all of this, another important thing, when we choose that particular node, we will choose the entire subtree, right? So the score of the node is not complete without also adding the subtree size. Score node is equal to score of node plus subtree underscore size of node, right? This is what we have to do. So this will just go through, do a dfs, and it will update it. And just to be sure that we got it correctly, let's do one thing. Let's print the score. Let's actually just print the entire score array, right? Let's print the score array just to see whether we got this correctly or not. Okay, right, we have made some mistake somewhere. Yeah, here it is where we have made the mistake. Score is equal to a list. Okay, now let's run it. Yeah, we forgot to put a colon. So again, why I like to just constantly run again and again is we get all of these issues out. Int object is not subscriptable. Okay, fair enough. Where is it trying to subscript something? Subtree size of node. We have made some mistake somewhere. Is it in the updating of it? Alright, yeah, we made subtree size is equal to 1. Ideally, it should be subtree size of node is equal to 1, not subtree size is equal to 1. Okay, so our output did not match. We are completely fine with that. But now look at this. We've got the scores, right? So 0 is 0. We don't really care about that. 1 score is 25. So we got the 1 score as 25, right? So that's encouraging. That means we're on the right track. The next one, 2 score, which was on the right side, is 7, exactly as we calculated. 3 is 1 because it's one of the leaf nodes. 4 is 9, exactly on the left side it was 4. Then you have like 5, 6, 7, 8 as 1, exactly how we calculated. And 9 is 5, which is also correct, I'm presuming. We go back, 9 we had as 5. Yes, 9 score was 5. If you can just rewind a little bit and check. 9 score was indeed 5. So our scores are coming correct if we start from 1. Okay, that's not what we want to do, but if we start from 1, we are going correct, right? So at least this part is there. And if you want to do brute force, all you need to do is right now go through all of the possible nodes there, all of the possible nodes, do a DFS from all of the possible nodes and find the maximum score that is there, and you'll get the answer. So that's the brute force approach, but we want to do it a little bit better. What we want to do is, okay, you did this, right? So we are printing the score array. Okay, great. Let's not do that. Let's instead do something like compute for. And what this compute for is going to do is it's going to try and compute for all of the remaining elements itself. Okay, so it's going to try and compute for the other elements that are there. Okay, so we did with 1, but now we're going to compute for other elements. Okay, and we'll actually start by computing with what this compute for will do. Let's again start with 1 minus 1. It's basically saying, okay, you take 1, we already know for 1 because we calculated for 1 already. Compute for all the neighbors of 1. And when you're computing for the neighbors of 1, compute for their neighbors as well. So we'll end up doing a DFS here also. But in this, okay, will we actually do a DFS here? No, we will not be doing a DFS here. I think it's more of a BFS. But anyways, I'll tell you my approach, what we want to do it over here as. So let's say, let's define this def compute for, and I'll explain what we're doing here. Node comma parent. Okay, and what we want to do is we'll go for a neighbor in adjacency of node. So for each of the neighbors in this node's adjacency, what we want to do is we want to check out, we want to do 2 things. Okay, make okay, first things first is if neighbor not equal to parent, because otherwise we don't want to go back again. We've already checked that, right? So make neighbor the entry point. This is what we'll do. We'll make neighbor the entry point. What happens if neighbor was the entry point? Then compute for neighbors, right? Okay, and then finally undo the change and go to the next one, right? So we're going to undo the change and go to the next neighbor. That's what we're going to do. So when we make neighbor the entry point, there are 2-3 steps that we'll have to follow, right? What are those 2-3 steps that we'll have to follow? So number 1 is, now that the neighbor is the entry point, what we're going to do is, before we go ahead, our node currently has to subtract the neighbor's score from itself. So we remove the neighbor's score from itself. Okay, and what we want to do is add that to the neighbor's score, right? So score of neighbor is equal to score of neighbor plus score of node. So what I'm basically saying is that now I'm going to come from neighbor to node in itself, right? So I'm going to come from neighbor to node and I'm going to do it. But that's not enough. We'll come to this one. Let's first update this completely. I want to make neighbor the entry point, right? So what I'm going to say is from node remove whatever was the score of neighbor itself, and also from node, apart from doing that, right? Apart from doing that, you also have to remove score of node. We'll also have to remove this. Score of node is equal to score of node minus subtree underscore size of neighbor. Okay, so we are not only removing the score of the neighbor, we are also removing from this particular node the score of all of the subtree size as well. So the score of selecting this plus also removing all of the subtree size itself. So we're going to do that. Now you can go ahead and do this. You can say that the score of neighbor. Okay, actually, sorry. Before that, let's come to the next part. Next, let's make sure the subtrees are correct. Let's make that both the subtrees are correct, and this ordering is very important, guys. I'll tell you exactly why this ordering is important, and it took me some time to figure it out as well. So I'll just give you the ordering that's here. So subtree size of node is this plus subtree size. No, first I remove the subtree size of the neighbor, right? So I'm going to remove the subtree size of the neighbor, and I'm going to add that to this subtree size of the neighbor. Now I'm going to enter into node using this neighbor, right? Earlier I was going from node to neighbor. Now I'm going to go from neighbor to node. So I'm going to remove all of the neighbor subtree, and I'm going to add that into the nodes. I'm going to remove that from node, and I'm going to add node subtree into neighbor. So I'm going to say subtree is equal to subtree of neighbor plus, what happened here, plus subtree of neighbor plus subtree underscore size of node. And this is also a subtree size, right? So yeah, this happened. Now finally I can recalculate now that both my scores are correct. So first what I did was I modified the node score. I then modified the node's subtree. Now I can modify the score. So I can say score of, actually we can start with score of neighbor. The score of neighbor is equal to score of neighbor plus now whatever is the new score of the node that we had earlier. So score of node, we can take that, right? Because we modified that score, we removed all of the influences of neighbor from that score, and now we can add that to the score. And the score of neighbor is equal to, also updated with score of neighbor plus subtree underscore size of node, right? We're going to add the subtree of node as well, right? So this is what it's going to do is, when you arrive at the next neighbor, right? So when you arrive, I'm going to go further deeper. I'm going to say recompute, what's the thing, sorry, compute for, I'm going to say compute for, now we're going to go to this neighbor and its parents is node. So basically what I'm saying is, now go further. Now you calculated what happens if this neighbor is the entry point. Now go further and check what will be the entry point if you check it for the next neighbor of neighbor. Okay, it's a bit confusing, guys, I know. Just try to take a pen and paper and see what's happening here. There's only so much I can explain. Basically what's happening is so what I did was, here was I recalculated for 4, and now that I've recalculated for 4, I say, okay, I'm not undoing it, right? I'm actually going to, okay, now that I know what's the score etc for 4, can you do it for 9? So when I'm doing it for 9, I have to use this previous score of 4 and say that, okay, arrive at 9. And when you arrive at 9, what is it for 8 and what is it for 7? So that's exactly what I'm trying to do over here, right? That is, I computed for this neighbor and node over here, and then I'll have to undo all of the changes. Okay, so to undo the changes, I'll first do this. I'll take this out, right? I'm going to take this, and actually even in that, so I'll just subtract these scores. I'll have to undo the change as we go back up the tree. Okay, so we're going to undo the change. And this, by the way, this process is called rerouting a tree. That is, if we change the root of the tree, then how it will happen. This process is called rerouting the tree. All right, so then we want to undo this as well. So we'll do this. So basically now the score of the neighbor, what you should do is, we added the score of the node. Now this time around, don't add the score of the node. Instead, subtract the score of the node and subtract the subtree size of the node. Then the subtree size of the neighbor has to be decreased first, right? Decrease this, and the subtree size of the node, now you can increase again, right? And finally speaking, this change can be undone as well, right? So this change can be undone exactly in the opposite way. Score of node is now score of node plus score of neighbor, and also the new subtree size of neighbor, right? So this is what we're going to do. So now what's going to happen is, notice one thing. I am already calculating the neighbor's score before I arrive at that neighbor, right? So the moment I arrive at a neighbor, which is when I enter into a particular node, see, for example, here when I had calculated already for 1. So when I enter into the function for 1, what's going to happen? I've already calculated for 1. Okay. Now what I'm saying here is, okay, now that you calculated for 1, go to the neighbor. First calculate it for the neighbor, which is exactly what we did here, calculate for the neighbor, and now go to that neighbor. So when I go to that neighbor, it would have already been calculated for that neighbor, and we're now trying to figure out for the neighbor's neighbor, and so on. So when I arrive at this function, I would have already got some answer for this particular parent, right? So for this particular node. So let me say that the max score for this node, okay, is equal to max of whatever the score for this node is, right? Whatever the score for this node is, and max score for this node. Okay, and what is max score? Let's create another thing here. Max score. This we'll create another one. So that is trying to take that for if we had taken each element, started each element, what would it be? So I'm going to just say this and say max score is equal to 0 into n plus 1. Great. All right, so we got this. So by the end of this one, we would have updated this max score node with, if each of these nodes were the starting points, then what is the max score for each of those nodes? So finally, we have to figure out our answer is equal to the max of all of the max scores that are possible, and you have to print that answer, right? That's what we have to do. Let's run it and check. It does work for this. Let's submit it and check. And yeah, it does work for all the test cases. So yeah, super difficult question. I know, a little bit difficult to understand. It's not that difficult to understand if you know this concept of tree rerouting. Basically, this is the crux of the question. Okay, we have already calculated for one. Now, if you want to go to any of its neighbors, we'll first calculate it for that neighbor, making that the entry point. So now our current node falls under the subtree of that neighbor. In that case, how will all of the scores change? So we change the score for our node itself. That's what we did over here. We change the subtree size of the neighbor and the current node, and then we updated the score of the neighbor. Once we did that, the score of the neighbor is sort of fixed, right? We go into that neighbor, and once we go into the neighbor, we say, hey, you know what? The score you are at right now is probably the max score for this particular node. See and store that in your max score array. Once you've done that, go further and try to keep making each of these neighbors as a as the main entry point. Finally, once you've done that, once you're recursing back, undo that change, because when you're going forward to other nodes, you want to undo this most recent change, and because the subtree will keep changing, so you have to undo that every time. So that's what we are doing here. So yeah, difficult question. I hope you understood it. If you didn't, watch this video again, take notes, especially take a lot of notes when we're talking about the trees and we're talking about the doing and undoing part of it, right? That's super important. So just to recap, that's what we did. We try to take we updated the score and subtree size of each of the components, and as in when we kept updating them, when we try to take every other neighbor as an element, as a starting point, and we try to go forward with it. So that's mainly it for the December daily challenges, everybody. I hope you liked it. I hope you can now proudly say that yes, I have done at least one problem of dynamic programming. That was our aim, to help you get accustomed to it. It's completely fine if you didn't get this day 5. It was a difficult question, but if you got it, great, good for you, right? So yeah, that's it from our side. Thanks everybody for joining. Again, a reminder, if you want to learn such complex topics, do sign up on our algorithms and data structures bootcamp, where I am the instructor and we have other instructors to help you with all of the product companies questions, previously asked questions. I want to congratulate everybody who participated in the December daily challenges, and whoever's on top of the leaderboard, will have a look and we'll let you know the winners as soon as possible. Thanks everybody for joining in today. It's been a pleasure to have you as part of these daily challenges. Until next time, do stay tuned for the January 2021 daily challenges. So until next time, we wish you all the best, and yeah, I'll see you all next time. Thank you everybody for joining in, and we'll see you all next time. Thank you.